Hi, my name is Walker Daniel. Today I'll be presenting my Lab 2 projectiles mission. The purpose of this lab is to compare the position of an object being thrown to a computational model with and without drag. The experiment, the object is a tennis ball that was tracked using tracker, and the computational model was created in GlowScript. This lab helps demonstrate Newton's second law. Newton's second law and other key principles. Newton's second law states that the net forces are equal to the change of momentum divided by the change of time. We can manipulate the formula to create the velocity update formula and the position update formula, as seen to our bottom left here. The first equation is the velocity update, the first underlined one, and the second one is the position. Um, Another key force is gravity, which will be um, negative gm, where g equals 9.8, and that is acting in the y direction. And then finally, drag force, which is created by an object moving through the air, hitting air particles, and it always moves against velocity, so it's the opposite. And it can be calculated with the formula B equals velocity squared, um, where B is the constant of proportionality. And looking at these, we and knowing what we know, we can tell that drag force does affect the object that we throw. For this experiment, a video of me throwing a tennis ball was recorded. Then it was uploaded to Tracker, where the position of the ball was marked frame by frame until hitting the floor. Then a computational model was created in GlowScript that could be changed to include drag or ignore it depending on what we needed. And then the trajectory graphs were all compared. So here's the video of me throwing the ball. In our objects, our observed results, we go into GlowScript here. Um, so as you can see, we track the ball frame by frame, just starting right when the ball is released and then ending right when it hits the floor right here. And here are graphs over here. Oh shit. And then here's our computational results. This top corner here is where we set all our conditions. The ball weighed 56 grams. Um, the initial position was 0, 1.7 in the y, and then 0 in the z. And the velocity vector, which is was calculated using the final positions in the initial positions as we saw originally with our update formulas. And then delta t was equal to uh, 0 point or 1.03 as seen here. That was the whole um equation here. And then yeah, this is where all the math happens. And these are our results. As you can see, the left one was without drag force, the right was with drag force, and the top was our observed values. As you can see, our observed and with drag force are very similar. Whereas without the drag force, the ball was able to move much further, seeing as there was no pull from the drag force moving against it. There were some possible errors, of course, tracking issues. As you can see, the ball was pretty small, and it's hard to pinpoint exactly the center where it was, especially when it was leaving and also when it hit the floor. And then, of course, frame limitations. Um, so we couldn't get the exact line. We could only get dots. And then finally, there could be possible z-axis movements that could have affected our calculations and causing possible errors. And here are some additional questions. Um, the first one asks um, about terminal velocity and if it was observed in our um, graphs, and if not, how could we change our experiment to show terminal velocity? But based on our graphs, we can go back. Um, they never really hit a linear trend. They are always moving somewhat exponentially, so they have not moved or they have not reached terminal velocity. But if we made the experiment taller, and gave it longer time, it would eventually hit terminal velocity. And then again, our second question is if the ball was thrown straight up with the same initial speed as your experiment, would this change anything? And it would take the ball longer to hit the floor, seeing as if we were throwing it with the same force upwards, all that momentum would be going up in the y-axis, making it um, move higher up and thus taking longer to hit the floor. Thank you.